Kaji sir.
Yes, sir.
Yes, sir. Yes, sir. Please.
Okay. Shall I start, sir?
Chandrajit sir, should we begin? I hope. Chandrajit sir, should we start?
Hello. Chandrajit, sir.
है मीटिंग में है.
Okay.
Yeah, hello.
Yeah. Okay, sir.
Yes, sir, I'm ready. Yeah.
Okay. Very good afternoon, sir.
Yeah, good afternoon, Kazi, sir. Yeah.
So on the behalf of SSBT's College of Engineering and Technology, Bambhori, Jalgaon, I NM Kazi heartily welcome today's speaker, Dr. Chandrajit Pal. I also welcome Dr. Zope, coordinator of this function, and I also welcome all the participants in the second session of induction program of machine learning and pattern recognition. It's my great pleasure to introduce such a nice personality and such a knowledgeable, high-profile personality, that is Dr. Chandrajit Pal. Dr. Chandrajit Pal did his BTech from West Bengal University of Technology in 2008. He completed his MTech in Information Technology from University of Calcutta. He secured the first rank in the university and got the gold medal. He completed his PhD degree from A.K. Chaudhary School of IT and University of Calcutta in 2017. His research interests include machine learning, computer vision, embedded system design, artificial intelligence, multimedia processing, approximate computing, etc. He is a peer reviewer for the journals like Signal, Image and Video Processing, Springer, International Journal of Electronics, Taylor and Francis, Defense Science Journal, DRDO, Government of India. On his name, 2 patents has been published. He has attended various international workshop and seminar. He has published so many papers in the international journals of repute. One of the paper, that is denoising filters for image enhancement, design and implementation, accepted for publication in Springer Nature Journal. Dr. Pal worked in various collaborative projects with DRDO, DST, Government of India and Redpine Incorporation. Dr. Pal received so many awards. Some of them are: in 2010, he got gold medal for the MTech University rank one. Then in 2011, DST Inspire Fellowship Presidential Award from DST ACRB Government of India. In 2012, VDAT Fellowship Award. In 2013, he got VLSI Conference Fellowship Award from Pune, India. In 2015, Newton Bhabha PhD Placement Award from University of Southampton, UK. In 2017, he have received ISCAS 2017 Conference Studentship Award. In 2017, again he got NPDF, that is National Post Doctoral Fellowship, DST ACRB Government of India Award. In 2018, AMD Best Project Award. The title of that project is Modified Huffman-Based Compression Methodology for a Deep Neural Network Implementation on Resource Constrained Mobile Platform. So, such a high profile personality is among with us. Now, I humbly request Dr. Pal to continue the session. Please come, sir.
Yeah, thank you so much, sir. It's my pleasure. Yeah, to be here.
Welcome,
Okay,
sir.
so today I'm going to discuss on the AI, the deep neural networks. Okay, I'll just first share my screen. Yeah. Okay, so is my screen visible?
Yes, sir. Yes, sir. Screen is visible.
Okay. Thanks. Okay, so here, so today we are going to discuss about the convolutional neural nets. So this is a part of the artificial intelligence, and this is like I mean one of the artificial neural networks. So there are various uh, artificial neural networks. So this particular neural networks deals with the computer vision data. So this is known as CNN in short, convolutional neural nets. So there are other various nets like sequential models like recurrent neural networks, and I mean various recurrent neural networks like bidirectional RNN, gated RNN, long short-term memory. Those were designed for handling sequential data, and this particular net is designed for handling the computer vision applications. Okay, like image, video, sort of things. Okay, so today, so the entire domain is the machine learning. From there, the subdomain is basically the AI. We know artificial intelligence. Within the AI, there are two things. One is the brain inspired, like within the brain inspired in the sense like the artificial neural nets, which is nothing but we try to mimic the biological neural nets, biological neurons, human neurons. Okay, so with that particular motivation, people tried to design. In late 1950s, okay, this research started to how to mimic the biological neuron and create the artificial neuron. Okay, so with that thing in mind, people have started designing and have been successful in mimicking. But however, human brain, as we know, is a much more complex thing. So the truefold, we cannot fully unfold the mystery of how human brain works. But to some extent, we have been successful. Researchers have been successful in coming up with the artificial neural nets. So, and it surpassed the human level accuracy in around the last half of this decade. Okay, so in identifying, recognizing the vision data. Okay, so almost we know that why today I thought of starting the convolutional neural nets, because these type of nets were designed to handle the vision data, and we know that computer vision is so important nowadays, because at any instant of time, the statistics says that almost 80% of the entire traffic, network traffic, internet traffic, okay, consists of the bits, okay, that consists of the vision data. Okay, at any instant of time, on an average, statistics says that 80% of the traffic, internet traffic, consists of computer vision data. Starting from means every day it's rising, and we can see that almost every households in here and you're nearby, you can see like the CCTV cameras. Okay, but just
Sorry to interrupt you, sir. Your PPT is not visible at my end. I don't know, is it for me, like for
okay,
all? Your PPT is not visible. I can only see the browser Cisco WebEx link.
Yes, same here.
okay, I'll just check it. Okay, thanks for informing. I'll just check it out, what is happening. Okay. Is it visible? Hello?
So
Is it
maybe it's
visible?
loading. It will take some time. We can see maybe it's loading. Like for now, black screen is there. Maybe like in few minutes it will load.
Okay, okay.
It's black screen only, sir, till yet. No PPT.
Okay. Uh, okay, let me check why it is like this. Acha, now check it, please.
Yes, sir, it's visible
Yes,
now.
sir.
Oh,
Yes, sir,
okay,
it's
okay,
visible now.
okay, okay, fine, fine, fine.
Please continue, sir.
Okay. Okay, so this is, I mean, I'm going to discuss about few applications of computer vision here. So feel free to interrupt me at any point of time if you have any questions. So the session should be interactive to make it more interesting. Okay. So this is one. The first image is elephant. Okay. So we need to classify. So this is basically an object classification problem. So we need to identify and classify whether it's an elephant or not, being like the binary classification, like 1 and 0. In the second picture, as you can see, I'll just put the laser pointer. The second picture you can see here is the object detection. So he is Dr. Govinda, one of my colleague. He is one of my colleague, Dr. Govinda, and here, I mean, after developing that application, we were testing in our lab in office. So this particular thing is doing the object localization. I mean, exactly where the object is, object identification. So this is telling this is a TV monitor, and this is a bottle. Okay, this is first of all, it is localizing actually where the object is in the frame. So then it is doing the, recognition. So object recognition. So this is TV monitor, this is bottle, and here the object is the face detection, followed by the identification of who the person is. Written here is Govinda. Okay, fine. So this is these are various, important applications of computer vision: object detection, object localization, object identification, and this is like another problem, which is generative with the help of the GAN network, the generative adversarial networks, which is recently used. We use the styles transfer with the famous Starry Night. So now I mean almost the things are happening in such a way that they are substituting the skill sets of the artists, human artists. Okay, so this is one picture and this is the background, and once we collage these two, this final image we get, so you get an impression as to an artist has drawn this picture, but actually it's not. It's a an output of the computer program, which is using GAN, generative adversarial networks, as one of its algorithm. So this is the picture and this is the background image. Once we collage these two, we get an output here. Okay, so now the question comes, why we need the convolution neural nets? Why we need CNN? So this is one of the example of a multi-layer perceptron, one-dimensional multi-layer perceptron, MLP. Those who are a little bit familiar with or know these things, it will be easy for them to grasp at present. Otherwise, please feel free to stop me, interrupt me, and ask questions. So here I'll explain the need of the CNN basically. So as you can see, these are input layer and these are the hidden layers. These three are the hidden layers and this is the output layer. And we get an output here, y cap is equal to A, the predicted output. And so the thing is here for a very small image, okay, so we are considering say 64 by 64 by 3. Why 3? Because RGB 3 channels. Total number of pixel here is 12288. Okay, 12,288 pixels. However, in practice, we don't use such small image. Okay, it's in the range of say for a 4K camera, as you can imagine, for a 4K visual CMOS sensor, we get a pixel range of the resolution is around 4K by 4000 by 2000. Okay, 4000 by 2000, and sometimes it's 2000 by 1000. Okay, and here we are using almost say 1000 by 1000. The image resolution is 1000 by 1000 and RGB, so 3. So this leads to 3 million pixels. just imagine 3 million pixels for a single frame. So when we process a video at in real time, say almost 30 to 35 frames per second, okay, so just imagine per second it has to process 35, I mean, this 3 million into 35. Okay, 3 million into 35, because each frame contains 3 million pixels. And if you are processing 35 frames per second, that means 35 into 3 million. Okay, so just imagine how much processing power your resource needs, your computational power needs. And I mean, it should be so powerful, and your algorithm should also be able to handle and extract the features from this kind of high resolution images. Okay, so the problem is, if we use a simple multi-layer perceptron, the problem comes in this way: when we are giving this input image to process. So this is x1, x2, x3 until xn. So where this xn is 3 million pixels, and here suppose we are using say 1000 hidden units, 1000 units in the hidden layer. Okay, so this is 3 million into 1000, that is 3 billion. Okay, so just imagine 3 billion parameters would come, okay, when we use a simple multi-layer perceptron to get an output. So one of the challenges of computer vision problem, that images can be so large, and we want a fast and accurate algorithm to work with that. Okay, for example, a 1000 by 1000 image will represent 3 million feature per input to the fully connected neural net. If the following hidden layer contains 1000, okay, units, then we will want to learn weights of the shape 1000 by 3 million, which is 3 billion parameters. So what does this parameter means? As to these are learnable or trainable parameters. That is, you train, and when you train a neural net, these parameters get trained. Okay, you need to, I mean, these parameters have got weights. Okay, like the coefficients we say, and we train these weights. The weights get updated every iteration of the training. Okay, only in the first layer. So just imagine, only in the if there are 1000 units per hidden layer, so only in the first layer itself we have 3 billion parameters, which is so computationally expensive. Okay, so one of the solutions is to build this using convolution layers instead of the fully connected layers. So these are the fully connected layers, that is, to each and every node it is connected to, each and every node is connected to all other nodes in the next to next layer. And similar it is true for every nodes which is connected to all other nodes. So these are called fully connected, that is each node is connected to every other node in its next layer. So instead of this, which was becoming very computationally expensive because of the huge number of parameters, so we can use convolutional layers instead. So let's see what are convolutional layers. So we do a problem of age detection. I think I mean, most of the people, they know what is an age detection problem, who has worked with computer vision or graphics, image graphics. Okay, so the convolution operation is one of the fundamental blocks of a CNN. And one of the examples about the convolution is the age detection operation. So it basically, what it does is it detects the ages of objects present in the image. Okay, so, and this is very important because the ages give the information. Ages is the first and the foremost I mean, a feature extractor which we get, and it's a very informative part which tells us about what the object is. Okay, the ages tells us about the nature of the object, about the type of the object, and I mean, about the object identification. It helps in identifying the object at the first go. Because say, for example, this is a car, and you get an outline of that car, so you can tell this is a car. You know, maybe you cannot tell about the company of the car or what type of car it is. That's a parsing structure. That's a tree. That once you identify that it's a car, then you further go into deep dive into it, and can tell that what is the car and which company it belongs to. That those are all like I mean, details about that car. But from the outline you can tell that this is a car. Okay, so that outline itself gives you the information regarding the I mean, identity of that, the label of that object. Okay, so that is also a very good feature. Feature set which helps you identifying the type of the object. Okay, so early layers of CNN might detect edges. Then the middle layers will detect parts of the object, and the latter layers will put these parts together to produce an output. Okay, so in an image we can detect vertical as well as horizontal edges or full edge detector. Now question is here, I mentioned one point that the convolution operation is a fundamental block of a CNN. So what is a convolution operation? So I'll just try to show a small animation here. Try to show a small animation here. You can see, 1 second here. Yeah. So as you can see, can you see my screen? So this is how a convolution operation happens. Okay, so that means it traverses. So if this is the image, if this is the image and this is the kernel, so the kernel traverses on the image, and the kernel has got its own weights. So it's if you use a a filter like a Gaussian filter or edge detection filter, where the weights are predefined. So once you traverse those weights on the pixels, so actually what the operation does is when the the filter, when it is at this particular position, in the first position, this particular position, what it happens is it multiplies the pixels with the filter weights, filter coefficients, 1 by 1, 1:1 operation happens. Okay, and then what it does is if the pixels at this position is say p1, p2, p3, p4, p5, p6, p7, p8, p9, and the kernel is said the w1, w2, w3, w4, w5, w6, w7, w8, w9. So the operation that happens is p1 into w1 plus p2 into w2 plus p3 into w3. In this way, when it chooses the first chunk, say 3 by 3 kernel, so it takes 3 by 3 pixels and the kernel 3 by 3. So 9 multiplication followed by 8 addition gives the resultant image, the resultant pixel here. As you can see here, this is the convolution operation which is happening. So this is a resultant image. The top green is the resultant image. When the filter traverses on the image in this way, it results in the resultant image in the green picture. It is showing the resultant filtered image, you can say. Okay, and what happens is here the stride, that is, it is moving, say one row at a time, one column at a time at first. See, then when it finishes this particular, reaches the boundary, it comes down by one row at a time. Okay, it traverses one column at a time, and then when it reaches the end, it comes down one row at a time. So here we say the stride is 1. These are very important terminologies to remember. While I'll be going to the deep architecture, you'll understand. So this is how this is what is called a two-dimensional convolution. Similar thing happens in a 3D convolution. Like the image is a volume, in that case the image, the 3D image, and this filter is also not a two-dimensional one, it's also a three-dimensional one. Okay, so try to imagine that the filter, it's a 3D filter, is doing the convolution in the same way, and the back in the volume also it is doing in the same way. So if I use a 3 by 3, here the filter size is 3 by 3. If I use a filter of size of a volume, a 3D filter of channel say 3, so the filter resolution will be 3 by 3 by 3, that is 27 elements, 27 kernel coefficients we say of that filter. Okay, and it will also take the same chunk of that image, that is 27 pixels, convert with the 27 kernel coefficients, and then it will do 27 multiplications and 26 additions to create one processed pixel. As you can see here, it is creating one processed pixel. So this is the filter which is traversing on the image, and as a result it is creating the processed pixels in the green portion. It is shown here. Okay, so this is what the convolution operation is. Which going back to my slide. Going back to my slide. Yeah. Okay, so here what happens is, in this way we use a deep neural network. Okay, and in the deep neural network architecture, I'll show you that these filters are present layer upon layer, layer by layer. That is, the image get processed at every layer, and as the processed images move down the architecture, okay, we successfully extract the more minute details of the images. Okay, that is, we try to extract the minute details starting from the beginning. So this is the image. As you can see, this is the particular image which is undergoing. This is a particular image of a car which we are moving, passing to a convolution neural net. The initial layer extracts out, this is the features after convolving with the filter weights. So you have to remember one thing: there are two separation. One is, once we use a pre-trained model, once we use a Gaussian filter or edge detection filter where the kernel coefficients are predetermined, which is following based on some equation, the filter coefficients we derived, and those filters we are convolving. But in case of neural nets, the same concept is the same, but the filter weights are not predetermined. We need to train the filter to get the predetermined weights. We need to train the filter. Okay, train the neural net. In other words, we need to train the coefficients of the filter kernels which constitute the neural net. Okay, with the training data set, to get those filter weights, we need to train it. Once the neural net is trained, then only the weights get freezed, and you can use those weights for your inference. Okay, to test the picture, to test the objects, you can test the objects to identify or classify the objects in your pictures, in your frames. Okay, so here, once we pass the picture of a car, we extract the high level features. Okay, so from these features you cannot identify this is a car. So it's like a some horizontal, vertical, diagonal edges. So the initial layers of the neural net extract these kind of features, and which is, from here it is very difficult to identify the class of the object. Okay, the identity of the object. Now, once these processed pixels move down to another level inside the CNN, convolution neural net, what happens? It extracts a little bit more in-depth features. As you can see here, the wheels, the doors. But one thing to identify is, from here also it is difficult to identify the class of the object. From here also you cannot conclude that it's a car. However, again, when these processed pixels move down the neural net another level down, so further these things are further combined. These parts are further combined to form the entire car. Now the windows and the wheels are again further combined to get the entire car. So from this particular picture, you can identify that it's a neural net. It's a car. Okay, that means slowly, once we are percolating the image deep into the neural net, we can identify by combining the high level features, the low level features. Slowly, we get the minute features, which assists us to identify the class of the object. So this is basically the class of the image. Okay, I mean it tells about the class level of that object. So in an image we can detect vertical. Now how in this way we can also train to find the edges of any image. Okay, we need to train, I mean we need to have a training data set where we can have the images as well as its edge detected counterparts. Okay, any image and its exactly equivalent edge detected counterpart. When we have this kind of training data set, we can train a neural net to identify not only vertical and horizontal edges but also edges present in any angles. Okay, this is one. Yeah, so so the thing is, suppose this is the picture and we try to detect the vertical edges. These are the vertical edges of this image and these are the horizontal edges, as you can see. So from this picture we can identify both the vertical and the horizontal edges. Okay, likewise we get some millions of pictures of this kind of pictures, millions of pictures, and its equivalent horizontal and vertical edges. Okay, to and we can train a neural net CNN to with this, and now in the testing phase we can give any kind of an image and it will be able to detect its edges. But however, initially how we can find out these horizontal and the vertical edges is we pass it through either Sobel, Previtt, several types of edge detection algorithms are there. We pass through it and we find out the edges in this way. Okay, and for those filters they have some predetermined kernels, as I will show you in the next slide. Okay, so this is a vertical edge detector. As you can see, this is a part of an image. So for simplicity, I have taken only a 6x6 portion of an image. This is a convolution operation. This is a very classical symbol which we need to recognize. And this is a vertical edge detector. These are some predetermined weights. Vertical filter of size 3x3. Okay, and it's the filter kernel is 111,000 -1 -1 -1. Once you convolve this with this, you get a processed pixel output, and here the equivalent command in Python is a conv underscore forward tensorfloat.nn.conv2d and is a keras conv2d. So these are the commands. Basically in Python, it's a like conv forward. In TensorFlow, it is tf.nn. Tf stands for TensorFlow. Nn is the neural net, and conv2d is a convolution, 2D convolution. Okay, and this is the keras. In keras, this is the command which is used, conv2d. Okay, convolution, 2D convolution. Okay, so these are the commands basically which we use to perform the convolution operation in Python, Keras, or TensorFlow. So okay, so this is a basic convolution operation shown. So how we perform is, suppose this is a 3x3 filter kernel, and you are convolving this 3x3 filter kernel here. We place it onto here. We place it here. So this multiplies with 255 plus 0 into 255. This minus 1 into 255 plus 1 into 255, 0 into 255. In this way, 1:1 operation happens. Okay, this with this, this with this, this with this, this 0 with 55, minus 1 with this. Once this happens, it moves down side 1 to the next column, moves down next column, and it repeats the operation. Again, it moves down to the another next column, and this is the final column. Okay, and then once it is done, it comes down to the second row, one row below, and it performs the same thing, after jumping one column at a time, and it at the same time it once first of all, this particular chunk, when this operation is done, it creates pixel X, as I have shown in that animation. Okay, in this way, this vertical edge detector works, and as a result, you get an output in like this. This is the image. Vertical edges, you detect the vertical edges. That is, there is a gradient, right? The change in the gradient. Okay, this is a contrast. This is a black. This is a white. So there is a gradient, pixel intensity gradient, we call it. So here it draws the edges. So these are the vertical edges. These are the horizontal edges. Similar way, we have the horizontal filter as well, and okay, so let's see this is an example of vertical edge detection. This is the image 20, 20, 20, all these, and these are all zeros. We convolve it and we create, this is a vertical edge detector. And what happens is, this is 20 and this is all zeros, which denotes this black zeros. I mean, when this particular image, say 6 by 6 image, when it is represented in the form of a image, and these are the pixels at the background of the image, and when it is represented, it is white, this is black. And when we convolve it with a filter, which is also in this way, it is shown, this 1 is white, 0 is gray, little bit gray, and -1 is full black, we get a vertical edge detector, I mean vertically edge detected image. So this is also an image. Since it is very small, you will not be able to see properly. It's a very small image where the middle elements are 60 and the side elements are 0. In other words, 0 stands for black, I mean gray, and 60 stands for white. So this is the edge. As you can see, this is the edge in between the two boundaries, two regions. This is the edge. So basically, if this image would be very large, then you would be able to identify the edge properly. So this is a very small portion of an image. That's the reason why you are seeing this edge in a very, you don't feel like this is an edge, but actually this is a very magnified, zoomed portion of a very small region, which is an edge. Okay, so suppose these are vertical edges. When you took a very small section of it, you see the middle portion is white and the dividing the two boundaries, which is black, two regions, which is black. So this is basically an edge, and this is all zeros. This is 60. So middle 60 is white, and these two zeros, so this is black. So this is an edge. Similar like this, when this is the image says all these are left hand sides are 0, this is a black, and right hand side is 20, this is white. When you convolve this, you get this output where 0 signifies the gray and -60 signifies the black. So this is also a kind of an edge. This is also an edge. This is a black edge, since these are -60 and has a sharp contrast with the zeros. The zeros are gray and this 60 is black. Okay, similarly, we can also do the diagonally, we can identify the edges. And okay, and so our neural nets will be learned or be trained to detect these edges. Okay, so not only vertical and the horizontal edges, but it will also be learned or trained to detect the diagonal edges as well. Okay, so it can learn to detect at any angle, like 45 degree, 75 degree, 24 degree, etc., etc. So here it is. Achha. Now, some basic concepts which we must know, like the padding. Okay, so what are actually padding? What does it do is, in order to to use deep neural nets, we really need to use paddings. So in the last section, we saw that a 6 by 6 matrix convolved with the 3 by 3 filter kernel gives a 4 by 4 matrix. If you can remember, here is a 3 by 6 by 6. Convolved with the kernel 3 by 3, it gives a 4 by 4. The mathematics behind that, I'll explain the mathematics behind that. So the rule which is governing is n minus f plus 1, n minus f plus 1. This is the final matrix, the resolution of the final processed image. Okay, so what does it do? What does it do basically? So when we get an image, say n by n with filter f by f, so 6 by 6 with filter is 3 by 3, we get an output in this way, n minus f plus 1, n minus f plus 1. So how does it do? How does it do is, suppose you are convolving this image. You are suppose convolving this image. this is the filter, and here you are convolving. This is a fast instant. Once we are convolving, you get a processed pixel here. This is a processed pixel. Next, you are convolving, you are jumping one column, and you are processing here with the same filter coefficient, and you get a processed pixel here. Okay. In this way, in the next turn, you will move filter one column here, and you will get the processed pixel here. And the next try, you will reach the boundary by one column, and you will reach here. Okay. Then what will happen? You will move this one row, it will come down one row, and the same thing will happen here, 3 by 3 again, and you will get here the processed pixel. Again one column right, you will get here. Again from here you will get one column right, you will get this, and finally this, you will get this. Again you will go one row down, and in this way it continues until you get this, 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 and when it reaches the last chunk, this one, this one, this one, this one, you get corresponding this, 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 this. So finally, the thing is, this is a 6 by 6 image, and this is a 3 by 3 kernel, and you are getting an output of say 4 by 4 output. Okay, so this is a physical realization, and the mathematics, the formula which is governing this is this one. So n is the 6 by 6, that is the image resolution. F is the filter size 3 by 3. So n minus f plus 1 into n minus f plus 1. Okay, when there is no padding. Okay, when there is a padding, that means padding in the sense you give here one more boundary here, one boundary you give, and you start from that boundary itself. That is why we do padding, to keep the output resolution same. That is, you can argue that when I'm using a filter of size 3 by 3 on an image of 6 by 6, I want a processed pixel of frame of the same resolution, 6 by 6, not 4 by 4, because it is decreasing, diminishing. You can see that image, the processed image, after applying that filter, the resolution is diminishing. This 6 by 6, this is 4 by 4. You can argue that no, I want 6 by 6 itself. I cannot tolerate 4 by 4. So in that case, we have to add a extra boundary here with padding it with 0 or some garbage values. Then you can start the filtering with from here. From here you can start, and you can encounter this padding. Okay, so with padding equal to 1, you can get the processed pixel of the same resolution that of the image 6 by 6. That's the importance of padding basically. So here, when we are not using padding, what happens? This is the formula. When we are not using padding, the formula burns down to n minus f plus 1. See, n minus f plus 1 when padding is 0. However, when padding is 1, we get n plus 2 minus f plus 1. So what it happens is, when f is equal to 3, say n is 6, the same example, I would like to continue with the same example for you to easily understand. When n, this is n cross n, this is f cross f. So when n is 6, basically, when n is 6 and padding is 0 in our example, what happens? 6 minus 3, f is 3. So 6 minus 3 plus 1, that is 3 plus 1, that is 4. Here also 6 plus 2 into 0, padding is 0. So 6 minus 3 plus 1, that is 3 plus 1, 4. So 4 by 4. we get an output of size 4 by 4. This is 4 by 4. However, if we want to get 6 by 6, we have to keep padding equal to 1. That is, we need to add a boundary here. So in that case, what happens? P equal to 1. So n is 6 plus 2 into 1, that is 2. 6 plus 2, 8 minus f, that is minus 3. Okay, that is 6 plus 2, 8. 8 minus 3 is 5 plus 1, 6. Here also 6 plus 2, 8 minus 3. So 8 minus 3 is 5 plus 1, 6. So we get 6 by 6. Okay. Similarly, whatever be the filter size, be it 3 by 3, 5 by 5, 7 by 7. If we want to get the same resolution as the output, same as the input, if you want to get the same resolution output image, processed output image with that of the input, you need to add padding equal to 1. So the formula burns down to n plus 2p minus f plus 1. Sorry. N plus 2p minus f plus 1. Similarly, here also n plus 2p minus f plus 1. Okay. So you need to remember that what padding we can add. So f is 3, so 3 minus 1. So here p is basically, if you write down in this way, that n plus 2p minus f plus 1 is equal to n, and so p is equal to f minus 1 by 2, where f is equal to 3. 3 minus 1, 2 by 2 is 1. Okay. So basically, to add the same value, to be the same resolution, to get the same resolution as the output, we need to add padding equal to 1. Okay. So if the filter is 3 by 3, then padding should be 3 minus 1 by 2, that is 2 by 2, that is 1. So if filter size is 5, that it is 5 by 5, then putting in this formula, it will come 5 minus 1 by 2, that is 4 by 2, that is 2. Okay, so padding we need to add 2 boundaries, not a single boundary, if the filter size is 5 by 5. Okay, so this thing you need to remember. That is, if we want to keep the padding, filter image resolution same as that of the input image, the output image. That means this would be like n cross n, because this is the output resolution. This formula governs the output resolution. Okay, that is this particular image. This particular image. So now this particular image, if it has to be same as this input image, that means this 4 by 4 has to be 6 by 6. That means, in other words, this particular expression, some expression into this expression has to be equivalent to 6. That is the reason why it is written here. N plus 2p minus f plus 1 is equal to n. That is, this should be ultimately n cross n. So putting here, we get padding is equal to n minus, this is basically putting here, we get nn, it is cutting out. So p is equal to f minus 1 by 2. So computing p from here, this equation, we get f minus 1 by 2. So that is, if f is equal to 3, then padding is equal to 1. If f is equal to 5, then padding is equal to 2. Okay. So now see from here, this stride is equal to 2 with stride, and here suppose the stride is 1. Here I'm assuming in this formula the stride is 1. Okay. Yeah, just a second. Yeah. So we talked about this use case. We talked about this use case when stride is equal to 1. So we did not put any parameter s here. We are assuming stride is equal to 1. So keeping divided by 1 is same as keeping this equation. Now that means stride is equal to 1 in the sense here we were moving one column at a time, and one upon reaching the boundary we came down to one row at a time. That means we are hopping one row and one column. Okay, there are cases when we need to hop two columns and two rows. So there what we had used is to the same equation, that is n plus 2p minus f plus 1, n plus 2p minus f by s plus 1. Here there in that equation s was 1, so we did not write the value of s. However, here we need to write the value of s, because if we write s is equal to 1, then there is no need of writing the value of s. However, if we keep the value of s is equal to 2, then there comes the need to write down the value of s. So that would be n plus 2p minus f by s plus 1. So here it comes like n is, suppose this is the example I'm showing, this 7 by 7, one image 7 by 7, and convolving with a filter of size 3 by 3 with stride is equal to 2. That means it is moving two column at a time. If this is the first instance, then the second instance will start from here, not from here. The second instance will start from here. And again, final instance will start from here. So it is jumping two column at a time. Once it reaches the boundary, it will not come down. In the previous case, it was coming down to one row at a time. Okay, if you remember. Now it will jump to two row at a time. That means the filter will traverse very quickly the image. Okay, so there are situations. So that is stride is equal to 2. So the final equation jots down to this. This is the floor function, not a ceiling function, that n plus 2p minus f by s plus 1 into n plus 2p minus f by s plus 1. So this equation governs the final resolution. So n here is 7 plus 2p, padding is 0, minus filter size is 3 by 3, that is 3, by stride is 2, plus 1, that means 7 minus 3, that is 4 by 2, is 2, plus 1, that is 3. So here it is 3 by 3. So the output is 3 by 3. Okay, so therefore it is 3 by 3. So these are basic operations we need to understand. Basic operations that we need to understand. Okay, summary of convolution, n cross n image with filter f cross f filter size with padding 2. Yeah, so the summary of convolution states here is n cross n is the image with filter size f cross f with padding p and stride s. Our output size is this. And this is the floor function, because if some fraction comes, we need to take the floor value of it. Okay, so this equation, no need to by heart or mug up this equation. If you understand the physical significance of how the filtering operation takes place, then it will be easy to equate. You can write down this your own equation. Okay, I mean this equation you can easily figure it out. So this equation governs the output resolution after filtering. So n plus 2p minus f by s plus 1, where n is the image resolution, p is the padding, f is the filter resolution, and s is the stride length. Okay. So any questions until now? I would love to answer. Any questions, please?
Yes,
No, sir.
participant.
Thank you.
If you have any question, then you can ask.
Okay, offline also we can take some questions, if not now. Okay, fine. So I'm proceeding. Okay. So there is one basic difference between cross correlation versus convolution. Actually, what we do is cross correlation, but the name comes as a convolution because it's like a 180-degree flip. Okay, how we do the convolution is like a 180-degree flip. We flip the kernel and do the convolution. This is just for your own knowledge, but conventionally we call it as a convolution operation. Okay. So how it happens, like when we do the convolution operations over volume, when we do the convolution operations over volume, like this is 6 by 6 by 3, this is 6 by 6, okay, image, and RGB, there's the red, green, and blue. So three channels. So one thing we need to remember is the filter depth. Okay, 3 by 3 is the filter. I mean the filter resolution here is 3 by 3, and the last cross 3. Why this is 3? Because we are using the 3 channels equivalent to 3 input channels of the image. So whatever be the one thing we need to remember, right? Whatever be the depth of the input image, the same depth you need to use in the filter during convolution. Okay, if we would have used here 6 by 6 by 6 channels, so here also you would have used 3 by 3 by 6. Okay, so the input image depth, whatever be the depth, so D is the input image depth. Here also the filter depth should be same. That is, if the depth is D, here we would have used 3 by 3 by D. Okay, or 5 by 5 by D. Here if it is 6 by 6 by D, then N by N by D. Whatever be the depth of the input image, you have to use the same dimension, and it will convolve over volume. Okay, it will take these 3 chunks and do the operation. Here it is 9, so 9 into 3, 27 multiplication, 26 addition to create 1 pixel. So you need to remember that in the output is again a 2-dimensional thing, 2-dimensional matrix which is created, not a 3-dimensional one. Because why? Because once we are convolving this, just to remember, once we are convolving this, it is convolving in volume. That you need to remember. Is convolving in volume. Okay. So how many elements, how many pixels it will take? 3 by 3 here, and 3 such channels. So 27. Here also 27 elements, as you can see. 27 elements, 3 by 3 by 3, 27 elements convolving with these 27 pixels to create 1 pixel. In this way, it will again traverse the next, okay, again traverse the next volume. In this way, it goes on to create individual pixels, okay, and the output resolution governing is the same. So 6 by 6 by 3, 3 by 3 by 3 to get 4 by 4 by 4. Okay, so the thing is, every convolution here, how many of multiplication you can see for 27 elements, 27 elements of the filter and 27 elements of the pixel. So 27 multiplication, because 1 by 1 multiplication happens, followed by 26 addition to create one processed pixel. Okay, so similarly, using multiple filters, what will happen, that you need to understand here. So slowly we are moving on to the neural nets, the architecture of the neural net. So here using multiple filters. So this is an input image. We are using 2 such filters. So one filter, we were using one filter 3 by 3 by 3. Here also 3 by 3 by 3. So for one filter, we are getting one feature map. We call it as a feature map. The processed image, we call it as a feature map. So for one filter, we are getting 4 by 4. For the second filter acting on the same image, we are getting again 4 by 4. So the output volume becomes 4 by 4, 2 4 by 4, that is 4 by 4 by 2. So this is the output volume we are getting from this output volume we are getting from 2 such filters. Okay. Okay. So So the governing equation is n cross nc, that is the input image, 6 cross 6 cross 3, and the filter is a resolution f cross nc. Nc remains same as I told. The filter depth should be same as that of the input image depth. This is 3 by 3 by 3, and we are getting an output n minus f plus 1, because here like stride is 1 by default. If we don't write anything, the value of stride, it assumes that by default the value is 1. So n and padding we are not using any padding. So n minus f plus 1, that is 6 minus 3, that is 3 plus 1, is 4 by 4 cross 2. Why 2? Because we are using 2 such filters. Individual resolution is 4 cross 4 cross 1, 4 cross 4 cross 1. When we are combining these two, we get 4 by 4 by 2. So this volume is an output of the simultaneous convolve operation of these two filters acting on the same image. Okay, so now how it happens, like as we know how a neural net works from the very beginning, like it's the equation governing is a wx plus b, where w is the weights of the neural net, and x is the input signal, and b is the bias, and the activation is the sigma. There are multiple activations. So if we see the basic architecture of a neural net, it is like this. Artificial neural net, there are two parts within a neural net. Okay, this is the x, this is the b, this is the bias, two things. So here the w is the internal weight of this neural net, w into x, it combines with this x, and addition, it takes a bias, adds a bias, and here is the activation. This part, second hemisphere, acts the activation function, that is wx plus b. This is the output. Okay, so this is basically, we call it as z, and here the output is sigma of z. Sigma is the activation function, be it whatever activation function it is. So output is sigma of z, where z is wx plus b. This is the output basically. Okay, so similarly here, when we do the operation wa, okay, so this is the ReLU activation function we have used. This is a general activation function, the symbol, whether you use ReLU, sigmoid, tanh, leaky ReLU, LU, whatever. Okay, and this is the WX basically, where and this is the input to the next layer. Okay, so that's why this is called an activation. So WX or WA, whatever you call it, plus this is basically the Z, as I told, sigma of Z. And this ReLU is the activation of this Z. So this internal part is the Z, that is WX plus B1, and ReLU is the activation. This is activation of Z. So activation of this entire Z, which is WX plus B. This is the WX plus B. This is internally plus B, and outside is the ReLU activation, and to get the final output here. Okay. So basically, what is W here is W is the filter weights, you can say here. A is the X, A or X. By activation from the first layer is going to the next layer, again the next layer. That's why it's written in generic term as A. So A is basically the input signal, which is the pixels here. Because input signal here is the image, and this is the weights are the filter coefficients. W into A, a convolving W convolve A, plus the bias. There is a tuning factor which we add to finally converge the training process of the neural net. So WA plus B, and then we finally give an activation onto this function to get an output processed pixel, or the feature map, we can say. So this feature map acts as an input to the next layer again of the neural net. Okay, so a very quick question. Suppose, please don't see the solution here. I just like to ask, like, the compute the number of parameters, which is very important for clearing the concept. So how you compute the number of parameters in a layer? Okay, so suppose we are having 20 filters that are 3 by 3 by 3, because here the filter is, see, we are using 2 such filters, each of size 3 by 3 by 3. Okay, here if we are using 20 filters that are 3 by 3 by 3 in one layer of a neural net, how many parameters the layer have? Say we are using 20 such filters, 20 filters, okay, 20 number of filters. Each filter is of resolution 3 by 3 by 3. So for a single filter, the solution is, for a single filter, the total number of parameters are 3 by 3 by 3 plus 1 is the bias. 1 is the bias. Okay, as you can see here, 4 by 4. We are using 2 filters here. The total number of parameters would be 3 by 3 by 3 plus 1 for the bias. This 1, this 2. So how many such? 2 such filters. That is 2 into, in bracket, 2 in bracket 3 by 3 by 3 plus 1. That is 3 by 3 by 3 is 27 plus 1, 28. So 2 into 28, that is 56. So we are using 56 parameters once we are using 2 such filters, each of size 3 by 3 by 3. Okay, that is ultimately is burns down to 2 into each filter number. How many parameters? Each filter 3 by 3 by 3 plus 1. So this 2 is basically n, that is denotes the number of filters. So here we are using 2 such filters. This is one filter, this is another filter. So 2 into 3 by 3 by 3 plus 1, that is 27 plus 1, 28. So 2 into 28, that is 56, equal to 56 parameters. Okay. Similarly, here when we are using 20 filters, each filter of size 3 by 3 by 3 plus 1, so 28. Each filter is having 28 parameters. Okay, now when we are using 20 such filters, that is 28 into 20, that is 560 parameters. So in any layer, if you have been asked that how to compute the number of parameters, which is very important criteria, once you are designing your neural net, is a very important criteria to know the number of parameters that needs to be present in a particular layer, because each layer consists of a set of filters. Okay, in this way. Okay, so hyperparameters. What are hyperparameters? Why the name hyperparameters? So, till now, what we saw, the filter coefficients are the parameters, which are like the trainable things, arguments, and hyperparameters like the batch size, the filter kernel resolution, okay, the step size, the learning rate. Those are the hyperparameters because it controls the learning of the parameters. Why the name hyperparameters? Because it controls the learning or the training effect. It affects the training process of the parameters. So those are called hyperparameters. In other words, it assists or it controls the training of the parameters or learning of the parameters during training process. That's the reason why they are called hyperparameters. Okay, so the bias, the activation functions, the stride, the padding, the number of filters, the filter size, those are all the deciding factors of how the training process will converge. So that's the reason why they are called hyperparameters. So we need to understand what is the basic difference between parameters and hyperparameters. It's a very common notation, which, okay. So a CNN example. So how a CNN looks like, basically, having understood till now the concepts of the number of filters, the parameters, the filter depths, the stride, the padding. Okay, so now it's time for us to start an example of a CNN. Okay, you can also design your own custom CNN. Okay, so let's see how things get designed. Once you understand this concept, you can design any CNN. Okay, you can understand any benchmark CNN and you can design your own CNN. If once you understand this particular concept. This way, suppose an input image of resolution 39 cross 39 cross 3 is an input image, and so 3 means 3 channels, and the resolution is 39 by 39, and we are using, say, 10 filters, each filter of size 3 by 3 by 3. Okay, stride is 1, and padding is 0. So given only this information, suppose I'm assuming you have been given only this information, you can compute the output from the knowledge you have acquired till now. Like once it is written 10 filters and f is a notation to write the filter resolution, f is equal to 3. So you will be able to know that what will be the filter resolution. The filter resolution is f3, means 3 by 3, and finally by 3. How? Because here the input depth of the image is 3. So here the resolution it is written given 3 means 3 by 3. But what will be the depth? Depth will be the same as the input image depth. Okay. So 10 such filters. So 10 such filters, each filter of size 3 by 3 by 3. Okay. So what will be the output? You are applying 10 such filters. In the previous example, you are applying only 2 such filters. Okay. Each of size 3 by 3 by 3. So now you are applying 10 such filters, each of size 3 by 3 by 3. What will be the output? See, the output is governing this formula. N is 39, padding is 0. Here it is given, padding is 0. F is basically 3. So n plus 2p minus f, 39 plus 2 into 0, that is 0, minus f is 3, by stride is 1. So s here is 1 plus 1. So this is 39 minus 3, that is 36. 36 plus 1, 37. So the output is 37 by 37. And by 10. Why 10? Because we are using 10 such filters. Remember, from here, if you are using 2 such filters, you are getting 4 by 4 by 2. Each 2-dimensional matrix output resulted from each filter. So number of filters governing the output dimension, output volume. Okay. So here 37 by 37 by 10. Why 10? Because you are using 10 such filters. And why 37? You got the reason, right? Why it is 37 from this equation. What will be the output resolution? Now, this is the processed image or the feature map after one layer of convolution. Now coming to the second layer. Now you have been given, say, 20 such filters. Okay, 20 such filters, each of size 5. Okay, let me write down here. So 20 such filters, each filter, what will be the resolution of each filter? Here it is given 5. So each resolution is 5 by 5 by, what will be the each filter resolution? 5 by 5 by 10. Because as I told, input depth should be same as that of the filter depth. Like the filter depth you will be taking same as that of the input image depth. So each filter is of size 5 by 5 by 10. And how many such filters? 20 such filters. Okay. So now put in this formula. N here is now 37, because this is the input image now. This is the input image now. So 37 plus 0, because padding is 0 here. Padding is 0 here. It is given 37 plus 0 minus filter is 5. Okay, 5 by 5 by 10 by stride is 2 plus 1. So 37 minus 5, that is 32. 32 by 2 is 16 plus 1, 17. So the output dimension is 17 by 17 by 20. Why 20? Because 20 such filters, each output from one filter. So this is the second output. So as you can see, the depth is increasing, the resolution is decreasing. See, 39 to 37 to 17. The resolution is decreasing, however, the depth is increasing. Again applying another set of filter from 17 plus 17 plus 20. We are again using filter of size 5 by 5 by 20, and number of filters say 40. Okay. So again putting in this formula, what it will come? That is 17 n plus 2p plus 0 minus 5 by stride is 2 here plus 1. 17 minus 5 is 12. 12 by 2, 6 plus 1, 7. So we get an output of resolution 7 by 7 by 40. Why? Because 40 such filters. Okay. So now it looks in this way. It looks like this. Again, the depth has increased. And now it's time to flatten it and do the fully connected before passing it to the final classifier. This is the softmax classifier. For softmax classifier is used for multi-class classification. Okay. So 7 by 7 by 40, if we serialize it, you will get, we need to flatten it. This is okay. I think some background noise is coming. Okay. So 7 by 7 by 40, once we flatten it, we get 1960 is many number of elements. And then we pass it to the final classifier to get the predicted output, y cap. Okay. This is how it works. This is a example of a simple CNN. Now there are various layers of the CNN. This is what I explained is the convolution and the fully connected. There is one more layer, is the pooling. And there are two types of pooling, basically max pooling and average pooling. So pooling works in this way. Pooling works in this way. It is basically used to reduce the dimensionality. That is, sometimes, I mean, in the initial layers, we use convolution, ReLU, pooling, and then finally the fully connected. So convolution, ReLU is the activation, and then the pooling. So how the pooling happens is, suppose we have a image of size 4 by 4, and we are using max pooling. What it does, by default here, the stride we take is 2. That is, we break it into equivalent chunks, 2 by 2, 2 by 2, 2 by 2, and 2 by 2. And from this 2 by 2, as the name indicates, max pooling means we take the maximum element from this pool, that is the 12. Again, from this chunk, we take the maximum element, that is 15. So from here, we take the maximum element, that is 23. And from here, we take 9. So we take the maximum elements from these chunks. Okay. And the filter size here is 2 by 2, as you can see. The stride is again 2 because after computing here, we jumped two elements, and we take this. We don't take this, otherwise the stride would have been 1. So after computing in this region, we jump into this region. So stride is 2, and the filter, we are considering this particular region 2 by 2. So the filter size is 2. So these are the hyperparameters, but here is no parameters are present because there is no trainable parameters. We are just shrinking down the resolution. Okay, this is called a max pooling. Another example is the average pooling, where we average down these 4 elements and we take the output. So if we average it, it will come 6 plus 4, that is 10. 10 plus 12, that is 22. Plus 3, 25. 25 by 4 is around 6.25. Here it will have been 6.25. So that's the average pooling. This is called max pooling. That is called average pooling. And so max pooling, how we do, when is the depth-wise max pooling? When we do it, we need to remember in this way. We need to we do it on individual layers when we do the max pooling. Okay. So suppose we come from here, the fast snap. If we take here, the max pooling gives 8 as a maximum element. Suppose in this way we continue and reaches the final block. Here also the max pooling is the maximum element in this colored region is 8. So here it is 8, and we do this on individual layers, that we need to remember. So if the number of input channel is NC, we need to do the max pooling on NC on each channel. Okay. And this is the average pooling, as I told, in this way. For every chunk, we average out all the elements that is present and we put the value here. Okay, so this is an example of a LeNet 5, which I keep for you as an assignment. Okay, this is the LeNet 5 example, and the paper is here. It is given here. I'll share the slides so you can get this information. The paper, the the complete paper of LANet 5. It was originally designed to find out that an example of MNIST data set, okay, 0 to 9, to classify the images of the numeric values from 0 to 9 in the postal code. And Jan LeCun is a godfather. I mean, he's a famous personality in this research domain. Jan LeCun. So he invented this particular LANet. Okay, from his name LANet, neural net. And 5 just got 5 layers. And if you understand this particular thing, this particular concept of a CNN, you will be able to understand this LANet architecture, which shows the convolution the same way, in the same evident way. It is written like a 5, filter size of 5, stride is 1. Okay, and here like the 28 by 28 input depth, here it's 6 such filters. Okay, so the filter is 5 by 5. Okay, and depth is 1 here, say 32 by 32. If you can use 3, then I would have written 5 by 5 by 3. Since it's only 32 by 32, I am writing the filter resolution as 5 by 5, stride 1. And how many such 5 by 5 filters? 6 such 5 by 5 filters. You will get an output of 28. Why 28? Because just think from here, compute yourself. From here, compute yourself. Like 32, there is n plus 2p, padding is 0. That is n plus 0 minus f is 5 filter by stride is 1 plus 1. That is 32 minus 5 is 27. 27 by 1 is 27 plus 1, 28. So this results down to 28. And as a result, we get here as an output feature map. We call it as a feature map, the 28 by 28. In a similar fashion, once we do the subsampling, that is a pooling. So from 28 by 28, definitely we will get 14 by 14, because the concept of pooling is, if it is 4 by 4, we burn down to 2 by 2. If it is 8 by 8, you burn down to 4 by 4. That is a subsampled. Okay, subsampling we call it. So once we do the pooling, again we do the convolution. So after pooling, we get a resolution of 14 by 14, and then after again we do the convolution with a filter of size 5. Okay, so that is 14 minus 5, that is 9 plus 1. Okay, 10, and 10 by 1 is 10. So you get 10 by 10 as an output. In this way, it carries on, and finally we take the fully connected layer. This is a fully connected layer. What we do here is, that is, initially I shown one example that if these are the input hidden layers, units of the layers, the fully connected layer means each module has connected to every other module in the next to next layer. In this way, it continues. And finally, there's a softmax classification. There are two types of things used for logistic regression. Is used for binary classification, whose curve is like this. That is close to 0, is close to 1. And softmax classifier, where the multiple, where it involves multi-class classification, we use softmax classifier. That is, it gives a probabilistic value, probabilistic distribution. Each element, it gives a probabilistic value. Okay, and the summation of all the elements will definitely burn down to 1, and that is a probability distribution, as we know. Okay, so this is one net, and the network architecture is down to here. Why 10? Because finally we got the 10 classes. So basically we use that 10 at last. It use the multi-class classification. It's 10. And okay, so the advantages: you can train your fast CNN. Here I have given some sample codes. Some sample codes are provided here. You can act on the CIFAR 10. Okay, and some benchmark neural nets are present. Once you install the TensorFlow with Keras, you can install and you can get some sample codes there, where some benchmark neural nets are present, like the AICTE-ISTE, whose architecture is this. Okay, AICTE-ISTE, followed by the residual blocks. There is the ResNet, the VGGs. Those are some basic block sets which are present. Okay, basic neural nets which acts on the ImageNet dataset. ImageNet dataset is around 400 GB dataset. Okay, so that has got 1,000 classes for classification, and these benchmark neural nets are designed to perform on, I mean, this ImageNet dataset, and it does the classification there. Okay, so this is just a brief overview of the CNN. Okay, I hope you got few concepts on this, and the rest depends on the practice that you do. Okay, everything is open source. You can use the Python with the TensorFlow, Keras, or the Cafe, or the PyTorch, whatever you feel like you can use. And if you have any questions, you can definitely question me offline. You can send offline questions. Okay, and I'll be happy to answer each and every one of it. Okay, thanks. I think, okay.
So, Kaji sir,
Yes, sir.
Yeah, sir, I think I'm done. If they
okay.
have any questions, you can please ask me now, or you can ask me offline, whatever.
Participants, if you have any doubt, then you can ask. Dr. Pal is ready to give the answer. I think there is no any question.
+1 is added. What's the reason, sir?
Yeah, hello, pardon, please. Hello. Hello.
Some places +1 is added. Some of the formulas. The main reason, sir?
Plus one. No, this is a plus bias, that we add a bias. Okay, so there's a bias that is used for fine tuning the training process, basically.
Okay, thank you.
So it's time to give vote of thanks. So I, N.M. Kazi, on the behalf of management and College of Engineering and Technology, Bambhori, Jalgaon, Maharashtra, I am very much thankful to Dr. Chandrajit Pal, as he has covered problem of the age detection, then learn to detect the ages, then very nicely sir have cleared the doubts of all the padding concept, then stride, then convolution operation over the volume, then concept of the filter is most important. The sir have explained very nicely about how to calculate the filter, 3x3 filter and other filters also. Then concept of the multiple filters, then filter calculations, pooling layers, maximum pooling, average pooling. Sir, you have covered very nicely. What a wonderful lecture I have heard today. So, on the behalf of college and Department of Electronics and Telecommunication Engineering, I am very much thankful to Dr. Chandrajit Pal, sir. Yeah, thank you very much, sir.
Thank you so much, sir. Thank you, everyone. Thank you so much, Kaji sir. Thank you so much, Pankaj sir.
Yes, sir.
Okay. We'll see again tomorrow.
Sir. Okay.
Yeah. Okay.
Yes,
Thank
sir.
you
Yes.
so much. Thank you.
Yes, sir. So now there is a break, lunch break. Okay. So all the participants are requested to take the lunch, and we will resume the meeting at 2:40. So all are requested to come at 2:40.
Yeah.
Yes,
yeah,
sir.
Yes, sir. Kaji sir. Yes, sir.
Okay.
Okay, sir.
Thank you very much.
Thank you, Kaji sir.